So now let's start adding data to our list, and let's start creating our list. Now you can create a linked list on the stack, but it's not meant to be created this way. The goal of linked lists is to create it in the heap so that you can manage that memory. The heap is basically a way for us to allocate memory dynamically. The way we access memory in the heap is through pointers. Let me draw what it looks like here. So this is our stack frame. At the bottom, it's divided into two, and this is overly simplified. This part is your stack, and this part is your heap. We can use, or we can create our linked list on the stack, but it's not meant to be created this way. The goal of our linked list is to be able to modify it and manage memory so that we can add or delete to it or to dynamically modify our list. And so we want to allocate it dynamically in memory. Now, in the heap, the only way that you can, so say for example, we create a new node and then you have your data. So the only way that you can access that is through pointers. So think of a pointer as like a remote control. Let's just say that this is your head pointer. Just think of this, and this may be a stretch, but if this is your television, you can use this remote control to control this or modify this television. And likewise, in order to modify this node, this memory that we allocated in the heap, you can use a head pointer to point to it, just like that. The pointer data type is basically an address variable. It holds addresses. So this head will hold the address of this newly created node in the heap. So the first thing I want to do is I want to create this pointer so that we can have a pointer that can point to our newly created node. I'm going to go ahead and delete this. And here what I'm going to do is it's going to be of our node data type. And our node data type is going to be a pointer, and we're going to call it head. So the head node is basically the first node of our linked list. And right now we don't have anything in the heap. We haven't created we haven't allocated memory. We have the structure or the blueprint to create a node, but we officially haven't created a node yet. We're going to create this pointer, and as of now, we're going to assign it to null, meaning it's not pointing to anything right now. So pictorially, this head node is just pointing to nothing. Okay, it's not pointing to our created node yet. And that's what we're going to do. We're going to create node using a heap, and then we're going to use this head pointer to point to it. What I want to do in order to create the node on the heap is I want to create functions. Sure, we can write all of our code inside the main, and I think that's called a monolithic way of coding. But you don't want 1,000 lines in your main function. So what I want to do is I want to modularize this a little bit and create a function. Since the compiler reads it sequentially from top to bottom, you want to create a function prototype. So I'm going to create a comment here, and I'm going to write all my function prototype here. And so what I want to call this function is, I'm going to use the word push. When we use the data structure of a stack, the operations that you would use on there are push, pop. So just to kind of get used to that language, I want to call this push. Our data type would be node. Remember, we type defed it. And I'm going to call it push, and I'm going to use a camel case notation, push head. Our parameters, it's going to be a node, but in order to utilize this, which is a pointer, we want to use a call by address. In order to do that, a pointer holds an address of a non-pointer variable, but a double pointer holds an address of a pointer. We're going to call that head, and then here we're going to create a parameter to insert our data. And that is going to be our first function prototype. I'm going to copy this so that we can create a definition for it, and I'm going to put it down here. So now we can start creating our first node in the heap. Here we are going to create our definition. The first thing we want to do is we want to create this node in the heap. At the bottom, we have a pointer. Let's just call this head. Our head right now is not pointing to anything, so we want to create a node in the heap. And to do that, well, we want to use malloc, and malloc stands for memory allocation. The first thing we're going to write is node, and then we'll call this new node. And here I'm going to use a snake case notation. And then we're going to malloc it. So we're going to say malloc, and then we have to give it the size. So we're going to do size of node. The size of our node includes the data, the pointer next, all of that. So this may be 4 and this may be 2 or 4 depending on your system. This should be at around 8 bytes or 16 bytes. This will work, but the malloc function returns a void pointer, so it's always a good practice to cast it. And so the way you cast it is we just want to put node pointer at the beginning. So now we want to be able to input our data. What we want to do is new node, and we want to use, because we are using pointers and we are using the heap, we want to use the arrow notation, not the dot notation. We're going to say data, which is this part right here, and we're going to, whatever the user enters for our data, we want to assign that to this. And then what we want to do is we want to assign this, we want to point this to our next node. Well, if we only have one node, we want to point it to null because it's not pointing at anything right now. So we have to define that. So now we created a new node, and we may also want to add an error and check here, because what if something happens to the memory and it's not allocated, or our memory is full, the heap memory is full, we haven't been using our garbage collection to clean it. The heap may not have enough memory. For our error check, we want to say if new underscore node equals null. So if it's null, we want to printf memory not allocated. And then after we print that, we're simply just going to exit 0. We're simply just going to exit our function. This is our error handling on lines 23. And then here we're inserting the data. So there's two conditions. What if we have our head, there's nothing on the list? Or the second condition is, what if we do have a list and we want to add to the beginning? So we want to address those two conditions. Let's address this first part. If head is null, then all we want to do is point it to this newly created node. Let's just say this newly created node is 100. What we want to do is we want to say head, and don't forget the star, and assign new node to it. So what if we have this condition where it's already pointing to a list? So what we want to do is, let's just say this has the data of 5, and then this is pointing to null value. And we want to create a new node. So let's just say that this is our new node. What we want to do is and let's just say that this is 200. For our next pointer, we want to point this next value to this address. Let's go ahead and code that. Else, we have to assign this next node to head. And in order to do that, we have to use the arrow operator, new node, arrow next, and assign head to it. So now this is going to receive the address of 100, or let me change this arrow. So new node, so we're going to assign it to head, but remember our head pointer should always be pointing to the very first link on the list. And in this case, this is going to be our new head. We have to switch that. So for our next line, we have to say head, assign new node to head. So now what's happening is we want to, let's just say the address that is holding, it is going to hold that now. This is going to hold OX100, and this is going to hold OX200. So now we have created our first function. So let's test it. We know that since we're using a double pointer here, we're using call by address when we do push something. So let's create our push head, and then the first parameter is the address of head, because we want to do a call by address. And then the data that we want to insert is, let's insert 5. Let me compile this before we do anything, just to see if I made any errors. Oh, okay, here, new node anytime we make a new node, it has to be a pointer. So let me put a pointer right there. Let me draw it up for you. So whenever we create a new node is actually a pointer that holds the address of the new node that we created. So that's why it has to be a pointer, otherwise you'll get an error. You see where it says error invalid initializer? All right, now that I've fixed that, okay. Here should be an underscore because I'm using the snake case naming convention. And now let's compile that. Okay, we are good to go. And let me double check. Now what I want to do is I want to clarify the difference between this head or this head pointer variable versus this head pointer variable. Okay, if this is your memory, let's just say that this is, the top part is the heap and the bottom part of the memory is stack. When we create a function, it goes on as an activation record, so this will become your main. And then inside of main, you have your head pointer. Now, once we create a function, and in this case, we created a function called pushhead, this becomes a different scope from main, but here we have our double star head variable. So this is a pointer, which is an address variable. And this is a double pointer, which is an address variable that holds the address of a pointer head. So what's happening is on line 23, we create a new node, which is a pointer. And then we malloc, or we use the function malloc to create a node inside of our heap. This new node holds the address of this new node that we created. And what's happening is when we call this function, we insert the address of this head so that this head holds the address of this head. So I'm going to draw that in a different color. I'll draw it right here on the side. So let's just say that head has an address of 100 and this head has an address of 200. So what happens is on line 17, when we add our arguments to our function, this head now holds the address of 100. So now this allows us to be able to modify the newly nodes that we create or the list that we create, because now this is essentially this head. So the next thing I want to do is I want to test our function to see if we really created a node or a head node with the data or the integer 5 inside of it. To do that, let me create a print function so that we can print our list. So what I want to do is, the first thing I want to do is I want to create a function prototype for it, and we'll just call it print list. This function will not return anything, so we're going to call it void. We're going to call it print underscore list. And then the parameter that we want to give it is we want to give it a node pointer head. You may be wondering why I'm only giving it 1 star, whereas in the previous function, I gave it 2 stars. Well, there's a big difference. In this function, I wanted to pass the address of head so that, right here, so that we can modify our list, our nodes. It allows me to manipulate or modify our node. Whereas this, we're not trying to modify anything. All we're trying to do is print our list. Let me copy this and go to the bottom. And now let's create a definition for it. So when creating this print list function, there are 2 conditions. The first condition is we have a head pointer that is pointing to null. And if that's the case, then this would mean that our list is empty. Let's address that condition. If head, and in this case, we don't have to put the star head because head is already an address variable. If head equals null, then what we want to do is we want to printf the list is empty. Otherwise, or else, this time I'm going to use the while loop because I want to traverse through each list so that we can print the data. We actually don't need this else. While head does not equal null. And what we want to do when it's not null, when the list is not empty, is we want to traverse through each node and print the data of each node. So we want to do printf. We want to do head data. So in the case where it's not empty, let's just say we do have a node. Let me create another node. This is pointing to this address. So that actually holds, and let's just say that this is 200. So this actually holds 0x200. What we want to do is we want to traverse, meaning visit each node. We want this head and we want to print out this data. So let's just say that this is 5, and maybe let's just say that this is 10, and then this is pointing to null. So this will hold the null. So what we want to do next is after we visit this node, print the data. And so now we want to go to its next link, which is this node. We want to assign to head the next link, which will be next. And this ought to do it. Let me compile it to see if there are errors that was made. Okay, so we are good to go. So now let's print our list. And in this case, we push the head 5. So we should get 5. Print list, and then we're just going to put head. So there it is. We have 5. Okay, let's test this condition. And what I'm going to do is I'm going to comment this out. So in this condition, we should have an empty list. The list is empty. Since we're pushing to the head, we are pushing, or we are adding an element or a node to the beginning of the list. So let me push another number. So let's just push 10. 10 should go at the beginning of the list. The output should be 10 and then 5. So let me go ahead and build and run. Oh, we have an error. So I did something wrong. So let's figure out what the error is. Okay, so when we print this, we are getting some garbage values. And why is that? So let's go to our push head function. Here's the problem right here. We have to put a star in front of this head because we want the address. This double pointer is pointing to this pointer. Whenever you use a double pointer as your parameter, make sure that all of your head has a star. So when these junk values were generated, it was because I forgot to put the asterisk in front of the head. In our parameter, I'm using a double pointer, which is a pointer to a pointer. In other words, a double pointer holds the address of a pointer because pointers are address variables. To illustrate how these junk values were generated, to the right I drew a pictorial representation of a int variable, a pointer variable, and a double pointer variable. The int data, 5, is assigned or stored into data. The address of data is assigned or stored into pointer, and the address of pointer is assigned or stored into the double pointer variable. Obviously, double pointer has its own address here, but it's not relevant for this presentation since we won't be storing its address into a triple pointer. So when data is printed, the output is 5. And when PTR is printed, the output is the address it is storing, which is the data variable address, and in this case, 0, 100. When double pointer is printed, the output is the address pointer that pointer is storing, and in this case, it's 0, 200. So when I dereference pointer by adding an asterisk in front of it, this asterisk pointer essentially becomes an alias for data. So when I print star PTR, the output is 5. Likewise, a single asterisk double pointer, or DPTR, becomes an alias for the no asterisk PTR. So when I print star DPTR, the output is 0, 100, which is the address that PTR is holding. Now, when there is a double asterisk in front of DPTR, double PTR becomes an alias for star PTR and data. So when we print double asterisk DPTR, the output is 5. So with this concept in mind, below, the current pictorial is a representation of the function pushhead. In this function, we essentially have 3 variable pointers: a double pointer head, which is represented in blue, a single pointer head, which is represented in red, and the new node pointer. When we create a new node in lines 32 to 39, memory is allocated in the heap by malloc, which is a node that has its own address. That address is stored in the new node pointer variable. In line 41, this is addressing the condition of an empty list. If this is the case, that we have an empty list, what we want to do is assign new node, or the address of new node, into head. And because new node is already a pointer, it's already an address variable. So head now holds the address of new node, which is 0, 100. And head is now an alias for new node. So starting with lines 45 and then going to 47, where I made a mistake of forgetting to add an asterisk in front of this head variable, what's happening here is we already have a node in the list. And then we want to assign the new nodes next, right here, linked to head. But the problem here is because I forgot to put the asterisk in front of this head, as a result, a head without an asterisk is not an alias for the new node, as shown here, that we assign in line 43. Instead of assigning the actual address of the first node to our head, we assign the address of star head pointer variable address. So once we get to line 48, the address of our new node variable is assigned to the star or asterisk head pointer. But by this time, the data has already been corrupted with junk values, as seen here. And these are more than likely addresses, but they're junk values because of this one error. Let's compile and print it. There it is. So now we have 10 and 5. So let's add another one at the beginning. Let's just say 15. So now the output ought to give us 15 because we're pushing ahead. We're always pushing at the beginning. 10 and then 5. 15, 10, and 5. So there you go.